When it comes to division, it's not defined for matrices. So if we think about division from a scalar perspective, if I want to say 3 divided by 5, essentially I'm saying that I'm taking 3 and multiplying it by 1 over 5, where 1 over 5 is essentially 5 to the negative 1, or 5 inverse. We can't do this directly in matrices, but we can do this. So when it comes to division with matrices, we're not really talking about dividing, we're talking about multiplying by the inverse. So there's two types, there's right division and left division with MATLAB syntax. Left division or right division is normal division, A divided by B. It's essentially as if we said A times B inverse. So A times 1 over B. But instead of 1 over B, we have to write B inverse. We also have left division in MATLAB, and we'll see this notation a lot in the later half of the semester. But it's essentially if we said A inverse times B, or 1 over A times B. But we can't write 1 over A in matrices, it has to be A inverse. We can think about the inverse theoretically similar to a scalar, where if I take 5 times its inverse, I get the number 1 back. This 1 is essentially identity in scalar algebra. In matrix algebra, in linear algebra, we don't have a 1, we have what's called an identity, which essentially is the equivalent of 1. The identity matrix is just all zeros with ones along the diagonal. It's always a square matrix, and it's created using the I function. So I3 gives me the identity matrix for a 3 by 3, which looks like this. 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, where I have ones along the diagonal. Same idea here in scalar algebra matches what we see in linear algebra, where A times A inverse is equal to identity. In this instance, order doesn't matter. A inverse times A should also give me identity. So this inverse is something we're going to learn how to calculate. You can think about it as like 1 over a scalar number. It's related to identity the same way 1 is related to scalar numbers. There's lots of properties of the inverse. There's some terminology to know. Matrices only have an inverse if they are square, but not every square matrix has an inverse. Okay, so some inverses exist, some don't. The inverse exists if its determinant isn't equal to 0. We will talk about the determinant in more detail later on. If a matrix is invertible, it's called invertible or non-singular. If inverse doesn't exist, it's considered singular and non-invertible. Okay, so just some terminology for you guys to know. The formula, or one of the ways to calculate the inverse, is using this formula here. This notation here, A with these 2 bars on the other side, this is called the determinant. And then ADJ is the adjoint or adjugate matrix, this thing here. We're not going to go into essentially all the details about linear algebra, but just know that's what it's called. And the steps to apply this formula I've listed out here. Step 1, 2, 3. The first thing is to calculate the determinant. We will get into more detail in the later half of this semester. For this material, we're really only going to calculate the determinant of a 2 by 2. So if we have a 2 by 2, then this is my formula, where if A equals A, B, C, D, then my determinant is going to be A times D minus C times B. I like to draw a little fish. A times D minus C times B. So for this example over here, it's going to be -4 times -1 minus 2 times 5, or 4 minus 10 equal to -6. And it turns out as long as that number isn't 0, that means our inverse exists. Once we have the determinant, then we can find the adjoint or adjugate matrix. Once again, for a 2 by 2, it looks like this, where if A is A, B, C, D, then the adjoint is going to be these 2 numbers flipped, exchange places, so D and A flip along the diagonal, And then B and C stay where they are, they just change the sign. So for this A, my A adjoint is going to be the -1 and -4 switch places, and then 5 and 2 change the sign. Once I have those two pieces, I just plug it into my formula, where here it is, it's 1 over the determinant times adjoint. So I take 1 over -6 times -1, -2, -5, -4. And notice this is just scalar multiplication, where I just take this, multiply it by that, then this, then this, then this. And we will go through examples of this as well.